This is now the second question for FRQ part B. So all they give you really is this equation. It says the number of mosquitoes in a field after a major rainfall is modeled by function M. And this is our function right here. So it's the number of mosquitoes in a field. It's not a very good line, but if it does ask you for context, then you know what it's about. And then T is the number of days after rainfall ended, where T is from 0 to 18. So 0 to 18 days. Part A just asks you to use correct units, so you actually talk about the context, and interpret the meaning of m prime of 15 equals negative 171. So it's going to be the derivative, right? So that's going to be the rate of change. And instead of having t as just t, it's 15 here. So really you just have to kind of break it down. So t is going to be 15, and then this is the value, negative 171. So it's going to be the number of mosquitoes, because it's negative, decreasing, and then on the 15th day. So just put it all together in a nice sentence. So here you could just say at time t equals 15 days, the number of mosquitoes, let me spell this correctly, is, and then again, because it's negative, you're going to make sure you write decreasing. So in the field, to be specific, and then is decreasing. At a rate of 171 mosquitoes per day. So it's not that there's negative 171 mosquitoes, but it's decreasing at a rate of 171 each day, or at least on that day. So that's it for part A. Part B, it asks us, based on the model, what is the absolute maximum number of mosquitoes in the field over the time interval 0 to 18? So hopefully when you hear absolute maximum or minimum or just extrema, you're thinking of the first derivative of your function. So let me just write m of t. M of t is negative t to the third plus 12t squared plus 144t. So here, if I take the derivative, I'm not going to talk through this. Hopefully you know what that would be. Hopefully I did that correctly. So I'm going to see if I can factor out 3. Yeah, so I can factor out a negative 3 actually. So I'm going to make this t squared minus 8t and then minus 4, 24, 8. So 48. So let's factor this now. So here I could make this now t 12 and 4, so minus 12, t plus 4 here. So here's our first derivative. And so our critical points are t equals 12 and then negative 4. So we're going to create a sign chart, or I'm going to at least. And then we're going to plug in some values. So notice that there's a negative here, so be wary of that. If you plug in something super negative like negative 1 million, well, this first one, the negative 3, is going to give us back a negative always. Negative a million minus 12 is still negative. Negative a million plus 4 is still negative. So here we actually get a negative. Same thing here, negative. Plug in something like 0, you'll get negative again, and then positive. So this is going to turn into a positive here. And then plug in something super positive, very large, negative on the outside, positive, and positive. So it changes sign each time. Oh wait, whoops. So there. So what was the question asking again? What is the absolute maximum? So if I want to check a maximum, I really only have to check 12 here. I don't actually. You could have done this without the sign chart. You could have just plugged in 12 and -4. But here, I guess this helps because I have to plug in less numbers. So I'm going to check what my value would be for, I guess t. Whoa, for t equals. Let me do something real quick. Okay, sorry about that. So I'm going to plug in the value x equals or t equals 12 into my original function. So I would also plug in 0 as well, and then 18. So here, if I plug in 12, it's going to be quite a bit, but -12 to the third power plus 12 times t to the second power, and t should be 12 there, plus 144 times 12. So what you end up getting, well, luckily, I believe it cancels out. So you actually, if you can notice, this here is the same value as this, but except that one's negative, one's positive. So you really have to do 144 times 12, which is going to be 288, 144, so 1728. Okay. If you plug in 0, you're just going to get 0 here. Now plugging in 18, let's see, so -18 to the third power plus 12 times 18 squared plus 144 times 18. So you do have to do some work here. Okay, so 18 times 18, 64 plus 8 is 114 again, and then 18 as well. So you get 324, and then 324 times 18 as well. Okay, we'll just keep going. I mean, okay, never mind. Just keep going. So here, 8 times 4. Unfortunately, you don't get a calculator for this question. 32, 16, 19, 25 here, and then 324. So 5,832. So this is negative 5832 plus 12 times whatever 324 is, plus whatever this is as well. Actually, wait. Okay, I'm just trying to think of a different way of doing this, but if anything, you could just multiply it out and you'll see what you get. Okay, so just to save some time, I'm just going to use the calculator here. So 2592, 12 times 324. This is 3888. I don't think this is going to be a common type of thing you'll do on FRQs, a lot of calculations. But what you end up getting is 598. So in the end, your answer is going to be 12 here. So if I were to write my formal answer, the absolute number of mosquitoes in the field over the time interval 0 to 18 is M of 12, which equals to 1,728 mosquitoes. All right. So that one actually took a while. But again, for finding absolute maximums, you look at your critical points. You technically didn't have to do the sign chart, but I did it anyways. And then you have to plug in your endpoints. All right, so moving on, part C. So for what values of T is the rate of change of the number of mosquitoes in the field increasing? So this one, it's just phrased a little weird. It's asking when is the rate of change increasing? So in other words, it's asking about the second derivative. So here we have m prime of t is equal to negative 3t squared plus 24t plus 144. I guess the factored version would also work. Minus, what was it again? 48. So here you could just multiply, I mean take the derivative of the inside there. So m double prime equals negative 3 of 2t minus 8. And then if you want, you could multiply it back, but I don't think you need to, but you could. And so our critical point in this case would be, you can actually factor out 2. It would be 8 over 2, which is equal to 4. So let's check at what happens before 4 and then after 4. So if I plug in something like negative a million, you'll get something negative, but you're going to multiply that by the negative 3 on the outside, so it's going to be positive. And then here, multiply something by something really large. Well, you'll get positive there, but multiply back by the negative 3, so it's negative. So the question again asked, when is the rate of change increasing? So it's going to be from this interval over here. So just put that into words. So the rate of change of the number of mosquitoes is increasing for 0 to 4. All right, the reason why I didn't put from negative infinity is because of the context. It only starts at 0. So I only put 0 to 4. All right, last question here. So for D, it says for 0 to 18 for T, the number of bats in the field is modeled by a function B, where B is a function of the number of mosquitoes in the field. Based on the models, write an expression for the rate of change of the number of bats in the field at time equals A. Okay, so is modeled by the differential function B, or B is a function of the number of mosquitoes in the field. Okay. Okay, so this one's a kind of a weird question. But in other words, you have B It's a function of m here. So m of t. And so if you want to find the rate of change of it, this is really just asking us to do chain rule. So times m prime of t. And so what you get is b of m of a times m prime of a. And so that's all you really need for this one here. Weird question, but that's all you have to do. All right. So I hope that helped. If you need any other help, you can always let me know. But thanks for watching.